Lecture 21, Concepts and Categories. As we've seen, learning, perceiving, and remembering require more than just forming associations between stimuli and responses, extracting information from environmental stimuli, and reproducing information stored in memory traces. Rather, learning is a process of generating and testing hypotheses in which the learner tries to figure out what predicts what and what controls what in the environment. And perception is a constructive process in which the perceiver tries to figure out what is out there, where it is, what it is doing, and ultimately what it means. And memory is a reconstructive process by which the rememberer tries to figure out what happened in the past, where, when, and to whom, and again what it means. Thus, the basic functions of perceiving, learning, and remembering depend intimately on reasoning, inference, problem-solving, judgment, and decision-making. In short, on thinking. Nowhere, I think, is this clearer than with perception, which is dependent on the perceiver's repertoire of concepts stored in memory. As Jerome Bruner has noted, every act of perception is an act of categorization. In identifying the form and function of objects, which is, after all, the basic task of perception, stimulus information has to make contact with pre-existing knowledge. In perceiving, we decide how, in general, to think about the objects and events we perceive, how they're similar to other objects and events that we've encountered in the past. When we classify two objects or events as similar to each other, we construe them as members of the same category, an act which reveals a concept which is part of our semantic memory. A category may be defined as a group of objects, events, or ideas which share something in common. A concept is the mental representation of a category, abstracted somehow from particular instances. Concepts serve important mental functions. They group related entities together into classes and provide the basis in language for things like synonyms and antonyms, and also allow us to understand the implications of the things that we see. Now, technically, categories exist in the real world, while concepts exist in the mind. However, this technical distinction is difficult to uphold, and psychologists commonly use the two terms interchangeably. Some categories are defined through enumeration, an exhaustive list of all the instances of a category. A good example is the letters of the English alphabet, A through Z. These have nothing in common except their status as letters in the English alphabet, and if you want to identify this category, there's really nothing else to do except reel off all 26 letters. A variant on enumeration is to define a category by a rule which will generate all instances of the category. An example is the concept of integer in mathematics, which is defined as the numbers 0, 1, and any number which can be obtained by adding or subtracting 1 from these numbers one or more times. If you follow that rule, you'll generate all the integers, and you'll only generate integers. But by far the most common definitions of categories are by attributes, properties or features which are shared by the members of the category. Thus, to anticipate an example we'll give later, birds are warm-blooded vertebrates with feathers and wings, while fish are cold-blooded vertebrates with scales and fins. All birds share those attributes in common, and all fish share those attributes in common. And in fact, there are three broad types of attributes that are relevant to defining a category. First, there are perceptual features, physical features of the object, features that you can see or hear or whatever. Then, there are functional attributes, including the operations that can be performed with the objects or by the objects, the uses to which they can be put. Functional attributes are often used to define categories of artifacts like tools or vehicles. And finally, there are relational features, which specify the relationship between an instance and something else. Relational features are used to define many social categories like aunt, which is the sister of a father or a mother, or stepson, which is the son of one's husband or wife by a former marriage. Not all aunts look alike, nor do all stepsons, but all aunts share the relational feature that they are the sister of a father or a mother, and all stepsons are the sons of one's husband or wife by a former marriage. These categories are defined by relation. Categories are groups of objects that share something in common. But as psychologists, what we're really interested in is the mental representation of these categories, or the structure of concepts. The classical view of categorization was given to us by Aristotle in his treatise on categories, part of the Organon, from the 4th century BC. It was Aristotle who gave us the view of categories as proper sets. That's Aristotle on the right, next to Plato on the left, from Raphael's The School of Athens. According to the view of categories as proper sets, the objects in a category all share the same set of defining features. Defining features which are singly necessary and jointly sufficient to demarcate, to define the category. By singly necessary, we mean that every instance of a category possesses that feature. The feature must be present for the object to belong in a particular category. By jointly sufficient, we mean that every entity that possesses the entire set of defining features is an instance of the concept. The entire set of defining features are all you need to identify an object as part of a category. Examples of classification by proper sets include geometrical figures. Remember from your high school geometry, all triangles have three features in common. They're two-dimensional geometric figures with three sides and three angles. And all quadrilaterals also have three features in common. They're two-dimensional geometrical figures with four sides and four angles. Animals are also classified by proper sets. All birds are warm-blooded vertebrates with feathers and wings. All fish are cold-blooded vertebrates with scales and fins. In each case, the features in question are defining features that are singly necessary and jointly sufficient to identify an object as a member of a category. If you're a cold-blooded vertebrate with scales and fins, you're a fish. You're not a bird. And if you're a two-dimensional geometrical figure with four sides and four angles, you're a quadrilateral. You're not a triangle. According to the proper set view, categories can be arranged in a hierarchical system that represents the vertical relations between categories, producing a distinction between high-level superordinate categories and low-level subordinate categories, sometimes known as supersets and subsets. These hierarchies of proper sets are characterized by perfect nesting, by which we mean that subsets possess all the defining features of supersets. Put another way, we create subsets by adding one or more defining features to the set of features that define a superset. In this case, subsets contain all the defining features of supersets plus new defining features. So, in standard Euclidean geometry, the kind you learned in high school, and that's a picture of Euclid there from Raphael's School of Athens, there are four types of geometrical figures. Points are geometrical figures in no dimensions. Lines are geometrical figures in one dimension. Planes in two dimensions, and solids in three dimensions. So at this level of categorization, the geometric figures are classified depending on the number of dimensions they consume. Nested underneath this superordinate category of planes, that is two-dimensional figures, are subordinate categories defined in terms of the number of lines they have. Triangles have three sides and three angles. quadrilaterals, 4 sides and 4 angles, pentagons, 5 sides and 5 angles, hexagons, 6 sides and 6 angles, and so on all the way up. And nested underneath the category of triangle are additional categories defined in terms of equality of sides and angles. For example, classifying triangles by the length of their sides, we have equilateral triangles, which have 3 equal sides and 3 equal angles, isosceles triangles that have 2 equal sides and 2 equal angles, and scalene triangles that have no equal sides and no equal angles. Alternatively, triangles can be subclassified in terms of the size of their internal angles. Right triangles have one internal angle of 90 degrees, and oblique triangles have no 90-degree angles. And oblique triangles can be further subdivided into acute triangles that have all their internal angles less than 90 degrees, and obtuse triangles that have one internal angle greater than 90 degrees. Notice what we've done is to create subcategories by adding a defining feature. All triangles have 3 sides and 3 angles, but there are subordinate categories of triangles that are defined either by the length of their sides or by the size of their internal angles. And we could do exactly the same thing for 4-sided figures, quadrilaterals. All quadrilaterals have 4 sides, but the subcategory of trapezium consists of quadrilaterals that have no sides parallel. Trapezoids have 2 opposite sides parallel to each other, but not the other 2, and parallelograms have both pairs of opposite sides parallel. And parallelograms can be further subdivided into rhomboids, which have no right angles, rhombuses, a subcategory of rhomboids that have all 4 sides equal in length, and rectangles that have 4 right angles, and squares, a subcategory of rectangles with all 4 sides equal in length. Again, we've created subcategories of 4-sided figures, quadrilaterals, just by adding another defining feature, whether the sides are parallel or not, how many sides are parallel, whether there's a right angle or not, and how many there are. Another example of classification by proper sets is the biological taxonomy set down by Carl Linnaeus, a Swedish naturalist in the 18th century. Linnaeus first divided the natural world into 3 great kingdoms: animal, vegetable, and mineral. The animal and vegetable kingdoms were then divided into phyla. Each phylum divided into classes. Each class divided into orders. Each order divided into genera. Each genus into species, and each species into subspecies. In the Linnaean system, every living thing is known by its genus and species name. Thus, modern humans are known as Homo sapiens, our genus and our species. Technically, Homo sapiens sapiens. Each level of the hierarchy is created by adding one or more defining features to the level immediately above it. In this way, every species and every subspecies is identified by a set of defining features that are singly necessary and jointly sufficient to identify an individual as a member of one or another species. So all proper sets can be arranged into hierarchies of supersets, superordinate categories, and subsets, subordinate categories. Within each level of the vertical hierarchy, there are also horizontal relations between adjacent categories, between subcategories within a particular level of the vertical hierarchy. These horizontal relations between adjacent categories are governed by an all or none principle. Because category membership is determined by a finite set of defining features, and an object either has the features or it doesn't have them, then an object is either in a category or not. There's no halfway. There are sharp boundaries between adjacent categories, and there's no straddling the fence. So, for example, referring back to high school geometry, if you're a geometrical figure, you're either a point, a line, a plane, or a solid. There's no in between. And if you're a plane, you're either a triangle or a quadrilateral or whatever. And if you're a triangle, you're either an equilateral triangle or an isosceles triangle or a scalene triangle. And if you're a scalene triangle, you're either a right triangle or an oblique triangle. And if you're an oblique triangle, you're either an acute triangle or an obtuse triangle. You're one place or the other because each of these categories, each of these subcategories is defined by a unique set of singly necessary and jointly sufficient defining features. You either have the features or you don't, and if you do, you're in the category. And if you don't, you're not in the category. It also follows from the classical view of categories as proper sets that categories have a homogeneous internal structure. Because all instances of a category share the same set of defining features, it follows that all instances are equally good representatives of the category. They're all alike with respect to their pertinent defining features. So, for example, here's the entire set of quadrilaterals, four-sided planes. As far as the classical view of categories as proper sets is concerned, each of these examples is just as good a quadrilateral as the others. They're all equal because they all share the same feature of being two-dimensional with four sides and four angles. So, the classical view of categories as proper sets yields two procedures for categorization. If we want to define a category of objects, then what we have to do is to determine the set of defining features that are shared by all members of the category. On inspection, all triangles, no matter what the kind, will have two dimensions, three sides, and three angles. And on inspection, all birds, of whatever kind, will be warm-blooded vertebrates with feathers and wings. And if you want to categorize a new object into a familiar category, the procedure is only slightly more complicated. First, you use your perceptual apparatus to analyze the features of the object. Then you retrieve from memory the defining features of various candidate categories. Is the object a triangle or a quadrilateral? Is it a bird or a fish? Then you match the features of the object to the defining features of the candidate categories. And if you find a match, you simply assign the object to the appropriate category. So, if you encounter a new animal and you want to determine whether it's a bird or a fish, you first determine whether it's a vertebrate or not, whether it's warm or cold-blooded, whether it has feathers or scales, and whether it has fins or wings. If it's a warm-blooded vertebrate with feathers and wings, you call it a bird. If it's a cold-blooded vertebrate with scales and fins, you call it a fish. It's just that simple. The classical view of categories came down to us from the time of the ancient Greeks, and it's lasted a long time. It's certainly the logical way to go about creating categories and categorizing objects. But however logical it may seem, it apparently is not how the mind categorizes objects, because there are some problems with the classical view of categories as proper sets that seem to call for another view of categorization. For example, some concepts are disjunctive. That is, they're defined by two or more quite different sets of defining features. An example is the concept of a strike in the game of baseball. A strike is defined as a pitched ball at which the batter swings but does not hit. But a strike is also defined as a pitched ball which crosses home plate in the strike zone, which is defined as the area over home plate roughly between the batter's shoulders and the batter's kneecaps. But a strike is also a pitch hit into the foul zone, except for the third such hit, and any subsequent such hits. And finally, a strike is a strike if the umpire calls it a strike. And for that matter, even if a pitch falls within the strike zone, it's not a strike either, unless the umpire says it is. So we have at least 4 different definitions of a strike in baseball, and they don't have anything to do with each other. There are four different kinds of strikes, if you will, but these strikes have no defining features in common. Another example is jazz music, which comes in two broad forms, blues and swing. But these two musical forms are completely different from each other. Blues has one definition, swing has another definition, and they don't really overlap. Jazz can't be defined simply as improvisational music because there are other forms of music, like Bach's organ pieces and even some rock music, which also involve improvisation. And you can't define jazz in terms of its African American heritage either, because there are lots of white jazz musicians, and there are some forms of African American music, like gospel, that aren't jazz at all. Disjunctive categories are problematic for the classical view because objects are in the same category even though they don't share the same set of defining features. Another problem is that many entities have unclear category membership. According to the classical proper set view of categories, every object should belong to one category or another. But is a rug an article of furniture? Is a potato a vegetable? Is a platypus a mammal? Is a panda a bear? Is a pickle a vegetable? It's not at all clear. The problem is we use categories like furniture without being able to clearly determine whether every object is a member of the category. This matter of defining categories actually turned into a Supreme Court case. In 1883, the United States Congress enacted a tariff act which placed a 10% duty on vegetables but permitted duty-free import of fruits. The customs collector for the Port of New York declared that tomatoes were vegetables and therefore taxable. But the International Tomato Cartel, which really there was such a thing, sued. And the case, known as Nix v. Hedden, eventually reached the United States Supreme Court. The court, in turn, unanimously declared the tomato to be a vegetable, while knowing full well that tomatoes are fruits. Justice Gray, writing for the court, noted that, botanically speaking, tomatoes are the fruit of a vine, just as are cucumbers, squashes, beans, and peas. But in the common language of the people, whether sellers or consumers of provisions, all these are vegetables which are grown in kitchen gardens, and which, whether eaten cooked or raw, are, like potatoes, carrots, parsnips, turnips, beets, cauliflower, celery, and lettuce, usually served at dinner in, with, or after the soup, fish, or meats, which constitute the principal part of the repast, and not, like fruits, generally as dessert. Put more succinctly, you might say, if you put it on your cornflakes, it's a fruit. Tomatoes don't go on cornflakes, they're not fruits. And in 2005, the state legislature of New Jersey considered a proposal to have the Rutgers tomato, a variety of tomato, declared the official state vegetable. Advocates for the tomato, which included a class of New Jersey fourth graders, actually cited the Supreme Court case as justification. Which brings us back to a related problem with the classical view of categories as proper sets, which is that it's very difficult sometimes to specify the defining features of many of the concepts that we use in ordinary life. But since we use these categories in our ordinary language, you'd think we'd be able to define how they're structured. A favorite example from the philosopher Wittgenstein is the concept of game. A standard dictionary defines a game as a competitive physical or mental activity engaged in for amusement. But there are lots of games that don't fit this definition. In solitaire, there's no competition. In Ring Around the Rosie, a children's game, there's no winner. And in professional football, played and enjoyed by adults across the country, there's really no amusement. Professional football is work. So what makes solitaire, Ring Around the Rosie, and professional football games like poker and cribbage and Monopoly? It's hard to say. Here's another, more recent example. the concept of planet in astronomy. The standard dictionary definition of a planet is a celestial body that revolves around a star. And we all know the names of the planets in our solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. But the problem is that there are lots of other celestial bodies that revolve around the sun, but we don't call them planets. For example, meteors and comets. Now, meteors and comets are typically pretty small, smaller than a planet, but there are some objects in the Kuiper belt between Neptune and Pluto that are almost as large as Pluto is, like Ceres or UB313, sometimes known as Xena. Like the asteroid Ceres. We call Pluto a planet, but we don't call Ceres a planet. Why not? To make things worse, astronomers discovered another object in the solar system known as UB313, sometimes called Xena, that's larger than Pluto and even more distant from the sun than Pluto is. But we don't call Xena a planet either. So the question is, if a planet is a celestial body that revolves around a star, what makes Pluto a planet but not Ceres or Xena? Now admittedly, Pluto has some planet-like features. It revolves around the sun like the other planets, and it even has its own moon, Charon, just like most of the other planets have moons. But in the first place, Pluto's really small. It's bigger than Ceres, but it's not bigger than Xena. Moreover, Pluto has a very eccentric orbit. The other 8 planets all orbit the sun in a particular plane known as the ecliptic. But Pluto's orbit is tilted. It's in a different plane. Moreover, Pluto's orbit is highly elliptical, much more elliptical than that of the other planets, so much so that it actually crosses the orbit of Neptune at one point. None of the other planets do anything like that. The situation was resolved in 2006, though frankly not to everybody's satisfaction, when the International Astronomical Union voted to approve a new definition of planet that reclassifies Pluto so that it's not a planet anymore. Note that the new definition is organized around classical proper set lines. A planet, as now defined, orbits the sun. A planet is also round. It has enough gravity to compress its mass into a sphere. This aspect of the definition gets rid of Ceres as a planet because Ceres isn't spherical in shape. Moreover, according to the new definition, a planet has to have enough gravity to clear its orbital neighborhood of other objects. This feature also gets rid of Ceres because Ceres is in the asteroid belt. It's in an orbital neighborhood that's full of other stuff. It gets rid of Xena, which is part of another set of objects known as the Kuiper belt beyond Pluto, and it also gets rid of Pluto. Because Pluto's orbit crosses that of Neptune, it obviously hasn't cleared its orbital neighborhood. So the problem of defining a planet and figuring out whether an object like Pluto or Ceres or Xena is a planet gets solved by this new definition. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune are in. Ceres, Xena, and Pluto are out. But note that the new definition creates its own problems. We now know that there are lots of other stars that have celestial bodies orbiting around them. We'd like to call them planets, but we can't call them planets because the way planet has been redefined, all planets orbit the sun. The definition of a planet applies only to our own solar system. So what do we call these other things? Pluto and the planets are a case where unclear category membership and defining features conspire to make life very difficult for astronomers. But these are problems that really shouldn't occur at all if concepts and categories were really structured according to the classical proper set view. Yet another problem with the classical view is known as imperfect nesting. Remember from our discussion of the vertical arrangement of categories into subsets, and supersets, that subcategories are defined by adding one or more defining features to superordinate categories, with the result that subordinate categories are perfectly nested underneath their superordinate categories. But that turns out not always to be the case, so that the vertical relations between superordinate and subordinate categories is actually more accurately characterized as a tangled hierarchy, not unlike the tangle of wires that probably exists behind your computer or your stereo system. Here's a concrete example, in fact, two concrete examples. Imagine a three-level hierarchy in which animals are subcategorized into birds and mammals, and then birds are subclassified into sparrows and chickens, and mammals are classified into dogs and pigs. In a perfectly nested hierarchy, sparrows and chickens would have more features in common with birds than they have with animals, and dogs and pigs would have more features in common with mammals than they do with animals in general. So sparrows and chickens ought to be judged as more similar to birds than they are to animals in general, and dogs and pigs should be judged as more similar to mammals than they are to animals in general. But that turns out not to be the case. To begin with, most people judge chickens to be more similar to animals than they are to birds, even though they judge sparrows to be more similar to birds than they are to animals. Now, everybody knows that a chicken is a bird, of course, but people just think of chickens as more similar to animals than they do to birds. That shouldn't happen. Another anomaly comes from examining response latencies in a category verification experiment. In such studies, we ask subjects simply, is a sparrow a bird? Yes or no. Is a sparrow an animal? Yes or no. Is a dog a mammal? Yes or no. Is a dog an animal? Yes or no. The classical view of categories as proper sets predicts that it ought to take less time to verify that a sparrow is a bird than to verify that a sparrow is an animal, because the category verification process has to go through only one level rather than two. Same goes for verifying that a chicken is a bird as opposed to a chicken as an animal, or a dog is a mammal as opposed to a dog as an animal, or a pig is a mammal as opposed to a pig is an animal. It works out just that way for birds. It takes less time to say that a sparrow is a bird or a chicken is a bird than to say that either of them is an animal. That's just the way it should be. But the response latencies reverse themselves in the mammal case. It actually takes subjects less time to say that a dog or a pig is an animal than to say that a dog or a pig is a mammal. And again, this just shouldn't happen if categories are represented in neatly, perfectly nested, proper sets arranged hierarchically into superordinate and subordinate categories. This brings us to the last and in some ways the most severe problem with the classical view of categories as proper sets. The fact that some instances of a category are simply better instances of their category than others are. This is known as the problem of typicality. Sparrows are rated better instances of the category bird than are penguins or chickens or ostriches. Sparrows are just more birdy birds. And within a culture, there's a tremendously high degree of agreement about these typicality ratings. The problem for the classical view is that all the instances in question share the features that define the category in question, and thus, from the classical view, they must all be equivalent. Whether you're a sparrow, or a penguin, or a chicken, or an ostrich, you're a warm-blooded vertebrate with feathers and wings. You're a bird. And with respect to the classical view of categories as proper sets, all birds are created equal. But obviously, some birds are better birds, more birdy birds, than others are. Here are some examples of variations in typicality taken from a study by UC Berkeley's Professor Eleanor Rosch in 1975. The category of furniture is defined as movable articles that make a room suitable for occupancy or use. All articles of furniture do that. But subjects rate some articles of furniture, chairs and desks, as more typical of the category than others. Rugs, not very typical. Ashtrays, very atypical members of the category furniture. Sparrows are rated as highly typical birds, much more typical than owls, and certainly much more typical than chickens or penguins. Peas and corn are rated as typical vegetables compared to pickles, and oranges and cherries are rated as typical fruits compared to pickles. Note that pickles are equally bad instances of both the category vegetable and the category fruit. And in line with Justice Gray and the United States Supreme Court, tomatoes are rated more typical of vegetables than they are of fruits. You can see variations in typicality even when the category in question has a clear and obvious proper set structure. In a study by Armstrong and colleagues, subjects rated the number 4, a very typical example of the concept of even number, and numbers like 18 and 106 as less typical. The number 3 is a much more typical odd number than numbers like 501 or 447. Mothers and housewives are rated as more typical of the category female than princesses or even policewomen. And to put the icing on the cake, subjects rate squares and rectangles as more typical of the category plane geometry figure than they do circles or ellipses. All of these categories have a proper set structure, a classical structure. Everybody knows how each of these categories is defined, yet within each category there are differences among the instances in terms of how typical the instance is of the category in question. This again simply should not happen in a classical view of categories as proper sets. And these variations in typicality have a clear effect on the process of categorization. Here are the results of a category verification experiment in which subjects were presented with instances and simply asked whether they belonged in a particular category. Some of the instances were highly typical instances, like sparrows being highly typical birds. Others were low in typicality, like ostriches and penguins, not very typical birds. And other instances fell in between. Response latency, the amount of time it took subjects to verify that each object was a member of the category, varied clearly depending on the typicality of the instance. It took less time to verify highly typical instances than it did to verify highly atypical instances. But all these instances shared the same set of singly necessary and jointly sufficient defining features. If all subjects were paying attention to these defining features, there wouldn't be any typicality effects in categorization. So there we have a whole host of problems posed by the classical view of categories as proper sets. And if categorization proceeded by comparing the attributes of the object to some list of singly necessary and jointly sufficient defining features. Therefore, categories need to be represented some way other than as proper sets, and people must do something else when they induce concepts or deduce category memberships. Recently, another view of categorization, known as the prototype view of categories as fuzzy sets, has been introduced, originally by the philosopher Ludwig Wittgenstein on simply philosophical grounds, but it's gained status within psychology now on empirical grounds. According to this view, categories are not proper sets, but they're fuzzy sets, in that there's only a probabilistic relationship between possessing any feature and being a member of a particular category. No feature is singly necessary to define a category, and no set of features is jointly sufficient. Some of these features are central in that they're highly correlated with category membership. Most birds fly, but a few, like ostriches, don't. Most non-birds don't fly, but a few, like bats, not to mention Rocky the Flying Squirrel, do. Central features are found in many instances of a category, but in few instances of alternative categories. Other features are peripheral. There's a low correlation with category membership. The feature occurs with approximately equal frequency in a category and in its contrast. For example, birds have 2 legs, but so do apes and humans. Category members appear to be joined together not because they share a single set of defining features in common, but rather by a principle of family resemblance. Members of a family share lots of features with other family members. You may have your father's nose, your mother's eyes, your aunt's hair. Similarly, members of a category seem to share a family resemblance. Some instances look like other instances, but not all instances share the same features in common. In this view, categorization is based on the similarity of an object to the category prototype. Objects are assigned to categories if they have many features that are central to category membership and few features that are central to membership in contrasting categories. The fact that category members bear a family resemblance to each other, and that assignment to a category is based on similarity to some prototype, permits a considerable amount of heterogeneity within a category. And it means that some category members will be more typical of the category than other category members are. The prototype view of categories as fuzzy sets goes a long way towards solving many of the problems that beset the classical proper set view. You can have disjunctive categories because the probabilistic view allows you to have instances of a category that don't share any features in common with another instance of the category. That's an extreme case, and we'll return to the problem of disjunctive categories later. But at least the probabilistic view is not as troubled by the existence of disjunctive categories as the proper set view is. Unclear category membership is not a problem because, well, in the fuzzy set view, the categories are fuzzy. The boundaries between categories aren't clear and sharp. It's a matter of judgment. A tomato can be a fruit from one point of view, but it can also be a vegetable from another point of view. The difficulty in specifying defining features also flows naturally from the probabilistic view, because it's in the very nature of the probabilistic view that different instances of a category are not going to have the same features in common. There aren't any defining features, so it's not surprising that it's difficult to specify them. Imperfect nesting occurs because of variations in the number of central features possessed by various instances of a category. Some instances will possess relatively few of these central features, and they'll actually begin to look like instances of another category. And the most important problem of all, variations in typicality, is explained easily by the revisionist view of categories as fuzzy sets. If there's no set of singly necessary and jointly sufficient defining features shared by each member of a category, if category instances vary in terms of the number of central features they possess, then of course there are going to be variations in typicality. A sparrow is going to be a birdier bird than an ostrich is because it possesses more of the features that are central to membership in the category bird. The prototype view solves many of the problems that beset the classical view, but it has some problems of its own. And for that reason, other theorists have proposed an alternative exemplar view of categorization. According to the exemplar view, concepts aren't defined by lists of characteristic features any more than they're defined by lists of defining features. Rather, concepts are defined by lists of their members, with no defining or characteristic features to hold the entire set together. It's a little like defining a category by enumeration. The members may have some features in common, or at least probabilistically speaking in common, but according to the exemplar view, that's not important for categorization. What's important for categorization is that the members are examples of the category. So according to the exemplar view, concepts are represented as lists of their members, especially the very salient examples of a category. And when we want to categorize an object, we don't compare its features to a list of defining or characteristic features. We compare the object to the exemplars themselves. We call an item an instance of a category if it resembles, if it's similar to, some other object that we already know is an instance of the category. The exemplar view is particularly good at addressing the problem of disjunctive categories. Categories whose members don't seem to have anything in common, like the various kinds of baseball strikes, or the two kinds of jazz, blues and swing. That's because in the exemplar view there isn't a single unitary representation of the category that fits all category members to a greater or lesser extent. Instead, there are multiple examples of a category, and they don't really have to resemble each other. As long as the new object resembles at least one exemplar stored in semantic memory, you can place the object in the category. If it sounds like blues or it sounds like swing, you can call it jazz, even though blues and swing don't resemble each other. The prototype view and the exemplar view are great advances over the classical proper set view of categorization. But each of them has some problems, and from time to time psychologists will propose yet another view of categorization that tries to cope with them. This debate is likely to go on for a while. But this debate over the structure of categories illustrates an important difference between the purely philosophical approach to the mind and the empirical approach represented by psychology. Logically, perhaps, the best way to think about categories is that they're structured as proper sets, represented by lists of defining features. That was certainly the way Aristotle thought about categories, and that way of thinking carried the day for roughly 2,500 years, a pretty good run. But psychologically, categories seem to be structured quite differently, perhaps as fuzzy sets represented by prototypes or perhaps by collections of exemplars. In fact, we may have both prototypes and collections of exemplars in our heads at the same time. There's evidence, for example, that novices in some domain tend to classify by comparing new objects to category prototypes, whereas experts in that same domain will classify by comparing new objects to category exemplars. That's interesting, but the really important point is that the principles of reasoning do not necessarily follow the dictates of formal logic. You can't discover how the mind works just by using reason alone. You need empirical evidence. And when you collect empirical evidence, you're often surprised to discover that the mind works in a very different way entirely than what you'd expect based on logical reasoning. We'll see more examples of this general principle in the next lecture.